Good morning, and thank you for the opportunity to talk about geo-hydrological hazards in a global warming scenario, an issue that is getting momentum and increasing interest. The UN Office for Disaster Risk Reduction estimates that actually more than 90% of all disasters in the last 2 decades are or were, one way or another, climate related, including those caused by geo-hydrological hazards. And what are these geo-hydrological hazards affected by global warming? Well, they are actually many, and they include floods and flash floods, landslides and debris flows, permafrost melting, droughts, and others. And for the sake of time, today I will focus only on floods and landslides. And for this, I have organized the talk in 4 parts. First, very briefly, on climate, next on floods and then landslide, and finally a few slides of conclusions. So let me begin with climate. Well, to quote the IPCC, global warming is unequivocal. But the effects of global warming on geo-hydrological hazards remain somewhat difficult to determine and to project in the future. The IPCC mentioned floods and landslides a number of times in the reports. For example, in the report, Managing the Risk of Extreme Events and Disaster, one can read projected precipitation and temperature changes imply possible changes in floods, and also that changes in heavy precipitation will affect landslides in some regions. And of course, these statements are correct, but are somewhat vague, and I would add necessarily. So let me move now to floods. And what is a flood? Well, according to the European Commission, it is the covering by water of land not normally covered by water. And why should we care about floods? Well, because they are many and widespread. This map shows that more than 3,700 large floods globally between 1985 and 2010, an average of 143 events per year, one every 2.5 days. The map also shows that many floods occur where the population concentrates, and this is actually why we care. The IPCC has projected that the frequency of large floods, those with a return period larger than about 100 years, is expected to increase in many parts of the world, but particularly in Asia, Central Africa, and South America, and to decrease in Northern and Eastern Europe and in parts of North and South America. A problem with this projection is that our understanding of the effects of global warming on floods remains somewhat limited and conditioned by the number of climate-related variables that affect catchment and river hydrology. And the chart illustrates a web, I would say a complex web of hydrological and geological processes that control floods at different time scales. And the empirical data may actually not help us unravel the skein. The graph shows the annual peak discharge of the Danube River in Vienna from 1828 to 1900. And one may argue that the frequency of large floods, those that are marked by the red circles, was increasing at the end of the 19th century. But what if I extend the record to 2018? The complex link between climate and floods are somehow shifting the paradigms used currently in hydrology from a, let me say, more traditional view that consider floods as local, independent, random event whose magnitude is quantified by a stationary probability distribution based on relatively recent observation, to a perhaps more modern perspective that assumes that floods occurrence and magnitude depend on a network of long-term processes in the global atmosphere and in the catchment and the river system whose characteristics change in time, and they do it at different paces. A question to ask is to what extent flood hazard changes in response to global warming. This map shows the number of floods in Europe from 1985 to 2012, with events most frequent in England and then frequent in Central and Eastern Europe and in northwestern Italy in our Po River plain. This other map shows trends in flood peak in Europe for different periods, with increasing trends in central Italy and the UK, and in Central Europe, sorry, and the UK, and decreasing trends in Spain and Eastern Europe. More quantitatively, Bloch and his co-workers have recently examined discharge data for more than 4,000 gauging station, hydrological stations in Europe, and found a shift in the timing of floods, which they attributed to climate-related causes. Earlier floods along the Atlantic coast are due to earlier soil moisture maxima, and in northern Europe to an earlier snowmelt. Later floods around the North Sea are due to later winter storms, and around the Mediterranean to a stronger Atlantic influence in the winter and the early spring. A few studies have investigated the impact of floods on population, which is very important, and the IPCC, for example, projects that the population exposed to floods is expecting to increase globally, even if the variations are, in the estimates are, I would say, necessarily large. But the issue is really complex because floods vulnerability varies, for example, with income. In high-income countries, the losses dropped in the 70s and remain somewhat low, due mostly, of course, to mitigation measures. For other income classes, the trends really depends on a balance, a complex balance between economic growth and the ability to implement mitigation efforts. And please note that in low-income countries, mortality has remained high for long periods. And flood vulnerability, of course, can be reduced through a number of schemes, particularly adaptation and insurance schemes. However, extreme floods affecting simultaneously or nearly simultaneously multiple countries can stress the existing economic risk reduction and transfer mechanism, mostly through reinsurance. And I think we need better information on correlated losses to develop the insurance scheme that can cope with these extreme events. So let me now move to landslides, which are a rather neglected hazard. And again, what is a landslide? Well, it is the movement of a mass of rock, earth, or debris down a slope. Landslide can take several forms and occur singularly, like this one, the Oso landslide in the state of Washington in the US, which led to loss of life and destruction of private and public property, or they can occur in large, very large populations over areas of thousands of square kilometers, like these that were triggered by Typhoon Morakot in southern Taiwan in August 2009. And why should we care about landslides? Well, because they are also many and widespread. Between 2004 and 2016, more than 4,800 landslides, non-seismically triggered landslides, have caused 56,000 fatalities globally, an average of 4,300 fatalities per year or 12 per day. And the map shows that fatal landslides have occurred in all continents except Antarctica. This graph shows the annual rate of landslide with casualties in Italy between 1860 and 2014. Variations, as you see, are large, with oscillation that we think depend on climate and environmental changes and, of course, on societal changes, including the increased population. A question to ask is to what extent the landslide risk to the population will increase, will change in response to global warming. It is actually difficult to say because the problem is complex. There are multiple climate-dependent variables that can control or affect landslides, and because the temporal and geographical scales of climate and landslides are somewhat different. We reviewed the literature on landslide and climate from 1992 to 2016 and found that most studies were actually in Europe and Canada. We extended the review to cover 2018 for this conference and found additional study in South America, again in Europe, and in Southeast Asia. Italy is the most studied country, followed by France and the UK, all three of them in Europe. But large parts of the world are not covered by these studies, including Africa, Central Asia, Australia, and Japan. And here we show the expected changes in the abundance of activity of different landslide types as a result of the projected climate change. Most of the arrows actually point up, indicating an increase in the abundance or the activity of landslides, although there are some conflicting projections locally. In the review, we found that the studies were conducted using mostly three approaches: numerical climate and landslide models, empirical analysis of time series of landslide and climate data, typically rainfall or temperature, and analysis of paleo landslide data. And the modeling approach allows for projections, and this is why it is particularly interesting. They all adopt a similar framework that through a rather complex modeling chain obtain projection of the behavior or either a single landslide or even an entire landscape. And let me now show you briefly two examples. For a single landslide in southern Italy, Comegni and his co-workers have analyzed past records of annual precipitation and temperature that they used to calibrate a regional climate model that predicted a negative trend in precipitation and a positive trend in temperature, which they used to estimate a reduction of the groundwater table in the landslide of about 8 to 10 millimeters, so only this much. Then, using an empirical relationship linking pore pressure in the soil to the rate of deformation, they projected a decrease in the landslide deformation rate of about 10% per decade. By 2060, this corresponds to a total displacement of that landslide of 70, 80 centimeters, so really not much. So this study suggested that for this particular landslides will not be affected significantly by the projected climate change. And this, in a way, is important to design monitoring work for that particular landslide. Let me show a different example for a regional projection. For the upper catchment of the Tiber River that flows through Rome, 100 meters or a few hundred meters from us, we used rainfall measurements and synthetic rainfall projection to force a spatially distributed slope stability models. We used Triggs from the USGS, and we obtained two what we think are relevant results. First, we found that the size distribution of the projected landslide will not change in the future in this particular catchment. And this is important information for hazard modeling and risk assessment. However, our second conclusion, for the second conclusion, we found that the rainfall conditions that can result in landslides expressed by rainfall pressure are indeed expected to change, particularly from 2030 onward. And this is relevant, particularly for landslide early warning. These are operational forecasts we made using a threshold-based landslide early warning system on the left for the wall of Italy and on the right for the Gargano promontory in southern Italy, a very nice touristic resort along the Adriatic Sea. And for the Gargano area, the dots that you may see show where and when landslides have occurred in the period of our forecast. What is relevant here is that if global warming alters the thresholds, then this warning system will need to be readjusted and reconsidered. And indeed, we found in a different study that thresholds for meteorological domains differ in Italy. This suggests that where the meteorological regime will change in response to global warming, the thresholds are expected to change and the forecasting system will work. We are confident on that, but will need to be adjusted. Rapidly to the conclusions. I said before that the effects of global warming on geo-hydrological hazard remain somewhat difficult to determine and to project in the future, and I hope you better understand why now. There is a need to better understand and measure how climate-related variables, their changes and vulnerability affects floods and landslides and other geo-hydrological hazards. Without better understanding and improved modeling capability, it will be difficult to provide policy and decision makers and citizens with useful projection that will allow them to make informed decisions and take proper action. And what should we do? Well, for example, we need to expand our monitoring capabilities. All the rain gauges available to the WMO and the Global Precipitation Climatology Project today cover less than half of the surface of a soccer field globally. Not much to say that we know how much it rains, really. We need to enhance our ability to model impacts. It took weeks to us to prepare the regional projection for the Upper Tiber River Basin I showed you before, and that was for a single emission scenario. This is because we have slow computers, but also because our models are badly inefficient and we need better models in this field. We also need to bridge what I call the last mile, communicating more effectively to our fellow citizens how to cope with dangerous events. And we should also recognize that there will be different climate, floods, and landslide projection. And for this, I borrow from a paper of which two authors are here today in the room. They wrote, because it is naive to expect availability of trustworthy quantitative projection of future flood hazard, and I shall add myself landslide hazard, in order to reduce flood risk, and I add landslide risk, one should focus on mapping of current and future risk and vulnerability hotspots and improve the situation there. Finally, let me point you to this report of the World Bank where you can read, poor people suffer disproportionately and are more often affected by natural hazards. They lose more when hit by a disaster and receive less support to cope and recover. And I think as scientists, we should do our best to overcome this, frankly, unacceptable situation. Thank you for your patience.